And thank you very much for all the organizing for putting this workshop together. That looks very exciting. And also for giving me this opportunity to present my work. So on seeing the program, I added a first part on speed limits, and I postponed like what I had originally planned to produce about shortcut to adiabaticity in open quantum system in a second part. So there might not be time to cover everything, but that's not a problem. If you have any question, please do not hesitate to interrupt me. So quick introduction slides. I just moved to the University of Luxembourg from Bilbao, where I was co-leading a group with Adolfo Del Campo. And I'm now a research scientist since January in the University of Luxembourg. So it's a quite young university. I think it's not even 2 decades old. The physics department is now in the city center of the city of Luxembourg, and it's going to move in not far from the French border in Belval, where they are constructing the campus on an old industrial site. Very quickly, let me flash this announcement about the special issue that we are organizing with David Sueco on open quantum systems, and your contribution would be welcome. So here is the outline of the talk. So I decided on seeing the program to spend quite some time on speed limits, and I will actually quite give in some detail the quantum and classical speed limits. And then in the second part, I will talk about something totally different, which is about control of open quantum system and these techniques known as shortcut to adiabaticity, where I'll derive some general scheme and techniques to allow for control thermalization of system. And I will take the example of harmonic oscillator. Let me start with the notion of time in quantum mechanics, and maybe more than time, how fast can a process evolve? There's a long history about such kind of question that comes back to Landau, and I will highlight some seminal results, the first one being from Mandelstam-Tam, who derived the first bound on how fast quantum evolution can take place. That is given by the inverse of the variance of energy. Later on in 98, Margulis and Levitin developed another bound that was given as the inverse of energy. And it's only recently then these quantum speed limits, so-called, were opened and were extended to open quantum systems. We did some derivation of speed limits for the decoherence time, and I want to present the extension to classical system and how these bounds go through the quantum to classical transition. But before I do this, just let me flash again these seminal results. So in 1945, Mandelstam and Tam derived the first notion of quantum speed limits. They started with the Heisenberg equation of motion and a definition of time that would depend on the variance of the operator of interest. And they derived, in doing so, they derived a time energy uncertainty relation. So if you look at this equation, it gives you the time of a process as that would be bounded by h⁻², and here that would be 1 over the inverse of the variance in energy. So this derivation relies on the Heisenberg uncertainty principle. Later on, Margulis and Levitin developed another bound, and they looked at the evolution of a pure state. So looking at the amplitudes A, that would be the overlap between the initial and the evolved state, they found that this is bounded with the real part expectation value of this overlap amplitude is bounded by time tau, that's here as the inverse of energies. So in this bounds, one needs to define a notion of distance and how far is one state from another. And for this, I want to introduce the fidelity. So for pure states, the fidelity is just the overlap of, well, here I look at the initial state psi 0 and the evolved state psi t. So if we look at mixed states, well, we can also write this distance and this fidelity that is given in this sense here. Now, during the evolution, one wants to see how far we are from the initial state. So we can write the fidelity as 1 minus something that needs to be small at initial state, at initial time, and positive. So this something we can is actually what is known as the Burris length. So if I look at how far I am from my initial states, then this Burris length gives you this notion of distance. It is actually already bounded by the quantum Kramer-Rao bands that evolves like the quantum Fisher information. So here is the definition of the quantum Fisher information that takes the variance in energy. So for a pure state, taking the variance of energy through the Fisher information gives already a bound on how far we can go from some initial states. And this gives the notion of speed limit that is always in terms of some distance and some energy. So it can be average of energy fluctuation. It can be also notion of energies. And actually the two bands that I was presenting at the beginning, the Mandelstam, that would be this one, and the Margulis-Levitin were unified later on by Levitin and Toffolinis that proposed that the evolution of quantum system has to be, cannot be shorter than the quantum speed limit that is given by this distance over the maximum of this inverse of energy. So either the variance on energy or the difference between the average energy and the ground state energy. Right. With this, I need to say that there's an infinite family of bands in the sense that, well, first, it depends on how the distance are defined, but also it can be defined, like we can have an infinite family in terms of higher order of moments of the energy of the system. And what I want to present here is this bound quantum in nature? So the original one developed by Mandelstam is relying on Heisenberg uncertainty principle, which is basically quantum in nature. And the band derived by Margulis-Levitin also looks at amplitude of pure wave functions. And if you naively take the limits at h bar goes to 0 of this quantum speed limits, well, you also find that it goes to 0. So is it a pure quantum phenomena, and does it not exist classically? So to answer this question, I will look at a system in phase space. So, and here I define the fidelity in a phase space as a function of the Wigner function. So if we integrate the initial Wigner function and the time evolved Wigner function of a phase space, and this d squared gamma is 2 pi h by dq dp, I'll come back to this often. Well, this is how we define our notion of fidelity and distance between two states. The equation of motion for this Wigner function is given here, and it depends on the Moyel product. So that takes into account like derivatives in P and Q. And this HQP is the wild ordered Hamiltonian in phase-based. So if one can calculate on the basis of this equation of motion of the Wigner function, the derivative of this fidelity, and it just follows as the integral of the initial Wigner function times the Moyal product between the time-evolved Wigner function and the Hamiltonian. Now, with an integration by parts, one can push the Moyal product from the time-dependent Wigner function to the initial ones. And this is helpful because when we perform like Cauchy-Schwarz inequality, we can bound the derivative of the fidelity in this way. So the most important term that I will highlight and come back later here is this term. So it's the integration on phase space of the Moyal product of H and the Wigner function on times 0 squared. The reason that we can bound this is that the system is, well, the purity is always less than 1. So this is low, this term is lower or equal than 1. So the purity will be bounded by this new gamma that is this term here. If we look at this expression of the new gamma defined here for pure states, we find that back the results of Mandelstam in the sense that we find the energy variance coming back in this expression. So how to derive the split limit? Well, we can just integrate between 0 and time t, tau of the evolution, and then we find that the evolution cannot go faster as a distance, so 1 minus f over this new gamma that has a dimension of frequency. And here we have the equivalent of the Mandelstam type quantum split limit, but written in terms of Wigner functions. So again, we have this notion of distance, 1 minus f, it is sine square of the burst length between two states. And now the variance of energy is replaced by this new gamma that takes into account the Moyal product between the initial Wigner function and the Hamiltonian. So once we have this, oh, and let me mention here that this is one type of quantum split limits, but there's also an infinite family. So we can also look at different notion of distance in phase space or different distance in the space of density operators that will also give like a broader family of split limits. So I stick with this kind and look at how it goes through the quantum classical transition. So for this, I first expand the Moyal products in terms of H bar, and the first term gives us the Poisson brackets that I just give the definition back here. So if we look at this split limit in the quantum realm and replace the Moyal product by this Poisson bracket, then we find split limits in terms of the norm. Now, you can see that the frequency has become like a new gamma. That was the integration of this Moyal product of a phase space. We can write it as this norm 2, that would be now the integration of the Poisson bracket of the phase space. And this gives like the split limit in the semi-classical realm, where we still have the distance between two states, now in terms of the Wigner functions, over the norm that has the Liouvillin of, so the evolution of the initial Wigner function. At this state, let me highlight that we still have an explicit H bar in this expression. We actually have it in the norm that takes into account integration of a phase space that is 2 pi H bar dq dp. And we also have it explicitly in the Wigner function. So to go in the classical realm, we rely on like results that was derived by one of the organizers, Dennis van der, that is operational dynamics. And this gives us the equivalent of the Wigner function and in classical space, with here rho being the classical probability distribution. Importantly, in this equality, one finds again this 2 pi h bar that is appearing everywhere in the phase space integration. And one can interpret this 2 pi h bar as the area that is dividing like the phase space for the integration. So that comes back to the old quantization rule from Bohr-Sommerfeld, and where the phase space is divided into areas of minimal areas of 2 pi h bar. When we use this, well, the normalization is straightforward. We had before the Wigner function squared over this element of phase space and equal to 1, and now we have just dq/dp, the classical probability distribution function equal to 1. So when using this relationship to translate the Wigner function into the classical probability distribution, then one can write the fidelity that we had originally in the pure quantum realm as function of, well, we can get the classical equivalent, which is known as the Bhattacharya coefficients. And where instead of having the Wigner function, now we have the square root of the classical probability distribution, dq over the phase space. So there's no more h bar here. The Burris length that we had, so how far we are from this fidelity being equal to 1, then becomes like, instead of r cos square root of f, becomes of the same form, but now the fidelity is replaced by this coefficient b. So we now have all elements to write the split limits. So instead of having the Burris length here, we have this length in the classical realm between two classical probability distribution. And what was the equivalent of the energy variance for pure states, so or the given by this Moyel product here, we have it in the classical realm by this operative here. So this gives a bound on how fast a classical system can evolve. Let me just flash for completeness the semi-classical one that still has some h bar limit. So in doing so, in writing like the Wigner function as function of classical probability distribution and expanding the Moyel bracket through present brackets and getting the classical dynamics, we see that this quantum split limit that would have had a h bar limit equal to 0 is actually not 0 in the classical realm. And there is also a bound on how fast a classical system can evolve. This bound always has the same structure in the sense that it is some length divided by some energy variation, fluctuation. And this is the one that we propose that is of Mandelstam type, but in the classical realm now. Just for an illustration, let me consider a time-dependent harmonic oscillator and calculate this bound. So the Wigner function at any time t can be calculated from that at time b with this at time 0, sorry, where the position is q over b and b is this scaling factor. So this scaling factor is solution of the Markov equation, and we choose the boundary conditions such that it can be expressed in this way. And without going into much detail, let me just give the results. If we consider a ground state of a harmonic oscillator with a classical probability distribution that is a Gaussian, and well, if you choose like correctly the variance in X and P such that the equivalence quantum classical then is fulfilled, we actually find the three speed limits are the same in the sense that the fully quantum, semi-classical, and the classical one are the same form. Here is an illustration of what we would find. So this is the weights of change of the fidelity of all these Bhattacharya coefficients. And this is the bounds that we find on the classical speed limit. So let me take this opportunity to say that we have a bound that is tighter, that is actually going like this, but for which we could never prove like the actual, I have a missing like inequality that I cannot prove. So I'm sure there's like we can define tighter bound. It's just like some missing step in the proofs. So if you're interested to know more about this, just let me know. Right. At this time, this is the end of my first part. So maybe if there are questions, I will allow for like the audience to ask questions now. And otherwise, I'll just move to the second part.
Seems there are no questions right now.
Very good. So let me go to the second part, which is quite different, and it's on more like control of open quantum systems. So I will be looking at dynamics of open quantum system in general and how we can design scheme and protocols to control them through this shortcut to adiabaticity. I like to motivate these topics through like the classical picture. So shortcut to adiabaticity, you might have seen this picture before. It's basically tailoring excitations. So, and the classical picture would be that of a waiter that just goes like through a train trajectory, a trajectory that allows to have like no spilling out of the champagne at the end of the trajectory. So you can create excitation during the transients, but at the end, you reach a state that you would have reached by going adiabatically. This is particularly relevant in the framework of quantum thermodynamics. So, and here is a scheme of a heat engine that goes through strokes of like expansion, heating, compression, expansion, cooling, compression, and heating. And if you can go through the process faster through one of these control schemes, you can operate your cycle at high power while keeping a high efficiency. So this is one of the motivation to develop such schemes. There's been lots of work to develop like the unitary strokes that would be like the compression and compression. And we are interested in doing like looking at the open case where your system is interacting with some reservoir, because this will allow to do like fast cooling or fast heating. So one of the techniques developed for the shortcut to adiabaticity is the counter-diabatic driving. And here is how it goes. Imagine that you are driving your system with some time-dependent Hamiltonian that has some instantaneous eigenvalues and eigenenergies here. If you write the adiabatic approximation, it gives you like the solution of how your system is evolving. And the question is there a Hamiltonian H of t that allows to reproduce these dynamics? And allows, I mean, by this, I mean, even going faster than adiabaticity. So this was answered by Demir, Plug, and Rice in 2003, and later developed independently by Berry, that the answer is yes. So we can have such a control Hamiltonian that is given by the reference one, the one that is originally driving the system, and some correction. and the correction are dependent on the derivatives of the eigenstates, instantaneous eigenstates. This Hamiltonian basically gives parallel transport in the sense that each eigenstate is driven like along the trajectory with keeping the same populations. There's been a lot of work on both the theoretical and experimental implementation of this shortcut to adiabaticity. I will just mention very briefly the first experimental implementation with single particles that was then done in more complex system, first the BEC, where you can see in the controlled case compared to the reference dynamics. In the controlled one, there's no like sloshing of the BEC. There was also implementation in 1D quantum fluid, and I participated to do implementation in the strongly interacting Fermi gas. So this reference Hamiltonian here is given in the case that the system is closed, in the sense that there is no interaction with the system. And what we've been interested at is looking at the open system in the case that the system is interacting with some environment. There's been like intents to do this already in 2014 by Vacanti in the group of Vlachovedra that proposed control protocol for Markovian dynamics. And this scheme relied on the notion of adiabaticity in Liouville superspace. Then recently, like in the couple of years before, there has been like specific schemes for specific systems, and we proposed the one for general setup, which is the one that I will be presenting here. So we consider a trajectory that is arbitrary in the sense that it can have any, arbitrary in the sense that it can have any kind of coupling to an environment. And imagine that you can write this instantaneous eigenization with time-dependent eigen probabilities here, because the system is open. So the trajectory that we want to implement in the lab is described by this master equation, where we have the counter-diabatic term that would be governing the unitary part as presented before. But now we have a new term, that's this dissipator that depends on the derivative of this eigenprobabilities. So how can we implement this dissipator in the lab? We came with two physical scenarios, the first one being with gain and loss. So if you take a system that has a non-emission Hamiltonian, where the emission part is given by the counter-diabatic time-dependent Hamiltonian and some correction, non-emission correction gamma t, that depends on the derivative of this lambda t. Then we can just write the equation of motion. We get an anti-commutated term here. And if we normalize this equation of motion such it is trace preserving, then we arrive to something that was proposed by Brody and Graefe, that is balanced gain and loss. So in that case, this master equation that is non-linear in the states allows to reproduce this density matrix here, that is the originally targeted one. And for this, it requires implementation of this non-emission Hamiltonian. Now, if we look at mathematically, there's another interpretation that we can do for the same trajectory. So if we look at just the dissipator that is dependent on this derivative of eigenprobabilities, we can introduce a Lindblad kind of operator that would depend on the instantaneous eigenvalues, eigenstates, sorry, of this trajectory here. And we introduce rates that are dependent on the derivative of this eigenprobability. In doing so, we can rewrite the master equation in the Lindblad form, in the sense that, so the unitary is still given by this counter-diabatic Hamiltonian, the same as the one that would be obtained for a closed dynamic. And the dissipator becomes of Lindblad form. But importantly, this rates the gamma t are time dependent, and it is generally a non-Markovian master equation. Also, you can see that, so formally, we can write a master equation that allows for, well, reaching this trajectory, but you might think, how useful is it, in the sense that how hard is it to implement in the lab, because it requires instantaneous diagonalization of your trajectory. So this is a problem that already existed for unitary shortcut to adiabaticity. We find it here again for the open case, and I will illustrate an example of a harmonic oscillator, of how one can develop such a scheme for the fast cooling of a harmonic oscillator. So the system that I'm looking at is a time-dependent harmonic oscillator. And the question I'm asking is how to go from an initial thermal state to a final thermal state, but where I allow for changes in the temperature. So now, because we want to go in final state, in a final thermal state, we have to break this parallel transport, in the sense that we need to rearrange like the probability of distribution of the final, from the final to the initial state. And this is what we do thanks to the open process. So we want to reach this final thermal state given any initial temperature and any final temperature. We want to do it fast, or super adiabatically, or in a controlled time. And we want to find something that we can possibly implement in the lab. So let me first review the isolated case that is well known and that has been developed like in the past. So I will write like sigma, my trajectory of reference, that gives me like from I get you, thank you. So this trajectory that we want to implement is to go from this is to a time-dependent harmonic oscillator. So in that case, if the system is isolated, the counter-diabatic Hamiltonian is known and is the one that keeps the eigen state, so the Fock state of the harmonic oscillator, as solution of the dynamics, and this counter-diabatic Hamiltonian is just a squeezing term in X and P. To implement such kind of process in the lab, one would do another notation in X squared, so that allows to kill this squeezing term, and that's so we can the implementation of this dynamics, we can effectively implement the shortcuts in unitary dynamics. In that case, let me highlight that the von Neumann entropy of the system is constant. And let me introduce this constant epsilon as h bar omega beta. That is the one controlling the entropy here, as you can see here. So when the system is isolated, the time-dependent harmonic oscillator is the state will be just evolved according to this unitary dynamics. And here is a map of the states that we can reach with this kind of dynamics. So here is the final inverse temperature over the initial one, and this is the same about frequencies. When the product of omega beta is constant, there is no production of entropy. And in this sense, the family of states at which in this process are the one on the isoentropy line. The modulation of the trap that needs to be implemented in the lab is given by the reference one, and it's corrected by this scaling factor. That is the one that I was presenting in the former example, but the scaling factor is just like dependent on the initial frequency and this reference frequency. So imagine that you want to drive your harmonic oscillator through like some reference trajectory that gives you the omega tilt, But now you want to do this fast. You don't want to go adiabatically, but you want to reach the same state. So instead of using omega tilts, then you would need to implement this corrected frequency that is corrected by the scaling factor. If you have no dissipator, then you reach this kind of states that have a constant omega beta product. Now, let's say that your trajectory is open, and in that case, you have time-dependent eigen values here. In addition to what you had, like in addition of the counter-diabatic Hamiltonian, one needs to take into account like dissipation, because the entropy is now time-dependent. So the dissipator that we can engineer, we've seen before, it's just like the derivative of this eigenvalues. But in this particular system, we can write it as such. And the way we came up to find a form that you can implement in the lab is to dephasing in position. So what we do, and let me look at the same graph as we had before, but now for the open dynamics. So what I've done is just add a dissipator in the position. And now the family of states that you can reach are extended in the sense that you can do cooling and heating. And this is allowed thanks to changes in entropy, thanks to this control dissipator. So if I compare this with what we had before, the control frequency is given by the reference one, and a correction that looks like before we had the BT double derivative over BT, but now this correction is not just the adiabatic scaling factor, it also accounts for changing in the temperature. That is this additional term here. So first, when we open the dynamics, this changing the control frequency, and we have an additional factor, which is the dephasing. So we have a control dephasing that also depends on this reference frequency and this epsilon of t. So how it looks like if you were to implement this in the lab, well, let's say that you choose a reference frequency to do your compression protocol in that case. If you choose a final time, that's the schemes tells you like the control frequency that would need to be implemented in the lab here. Or if you choose to be faster, then you need like to have like faster kind of motion of your trap with even like trap inversion here. So that's for the control frequency. If we look at the dephasing, well, one can look at this gamma t, the control dephasing. So interestingly, the shape of this dephasing does not depend on how fast you go through the process, but only the maximum does. So this is a normalized gamma, and here in the end set we have the maximum. So if we go, the faster we go, this is the final time of your process, the faster you go, and the higher one would have to pay in terms of dephasing rates. So this is for a process that would give like phase space heating. So that would be in this orange box. One can do the same like for phase space cooling. And the most important difference here is that you need to implement negative dephasing rates. So if in the lab you can implement this negative dephasing rates, you can basically do arbitrary cooling while cooling in arbitrary time. Right, so how would you obtain this dephasing in position with the time-dependent rates? So we came up with two different options. One would be through stochastic parametric driving, the other would be through continuous measurements. And basically, one gets like a stochastic density matrix. And if you average over all realization of the noise, then we can realize this dissipation. Right, so I'll just flash very quickly these results and then come to the conclusion because I think time is over or soon. But so in that case, we looked at thermalization of a time-dependent harmonic oscillator. We can do like controlled heating and cooling. And this actually leads to squeezing. So it's well known that if you look at the time-dependent harmonic oscillator, you do have like squeezing in the X and P direction. But we were also interested to have like a control on the squeezing angle and how much correlation you put in the X and P coordinates. I will not detail these results for the interest of time, but I'm happy to do so if there's any question on it. Let me just come to the conclusion. So I started in the first part with the speed limit and showing how the quantum speed limits are actually not purely quantum in nature, but going through the quantum classical transition also, we find some classical speed limits. Then I looked at control of open quantum system and how to extend the shortcut to adiabaticity to a case with a dissipator, and showed like some application for the fast thermalization of a harmonic oscillator. With this, I'd like to thank my collaborator, highlight the poster by Adrian Juan Delgado that will be presented tomorrow, I think. And thank you very much for your attention.
Thank you very much for this very interesting presentation. I think that we have time for maybe 2 or 3 quick questions. Yes, please, go ahead.
Hi, thank you very much for an interesting talk. I just have 1 or 2 very quick clarifying remarks in relation to the first part of the talk. In the opening slide, you mentioned that for PT-symmetric system, the speed has got no upper bound. But what we have actually shown is a conditional result that if an observer had access to modify all the parameters in the Hamiltonian of a PT-symmetric Hamiltonian, then there's no upper bound in the speed limit. So it was a conditional statement. So that was the paper you referenced. But in a follow-up paper, I proved that, in fact, those parameters in Hamiltonian, which would give this power, so to speak, cannot be accessed by any observer. And therefore, the speed limit of PT-symmetric system is exactly the same as unitary system for a closed quantum system.
Oh, thank you very much for this. For this correction. I was not aware of this, so I definitely need to update and correct this.
And one other small remark in relation to the Fisher information, you mentioned about the variance, and that is indeed the case for pure state, but for mixed state density matrix, the Fisher information is not given by the variance. And this is sort of important from statistical point of view, because if one is trying to estimate the time parameter, if you have a stationary state, the Fisher information vanishes, but variance never vanishes if you have a mixed state. So
Right.
yeah, so in general, it's actually given by the Wigner-Janase skew information for mixed state, which reduces to the variance for pure state.
Right.
So,
Yeah. Yeah. Maybe I did not identify this well, but yeah, I did write the idea was to show the relation with the energy variance. So I did take the pure state case. But yeah, you're right. That would change for mixed state.
Any more questions? So maybe a quick question from me again regarding the first part. So again, regarding mixed states, actually. So in the definition of distance measures, there is some ambiguity on the quantum side regarding mixed states, right? To what extent does this carry over to the classical limit? Right, it seems that in the classical limit, like the distance definition is unique again, right?
Yeah, so even on the classical side, you can have different notion of speed limits according to which distance of state you choose. So of course you can go like, even if you look at just like a two-level system on the Bloch's field, you have, as you mentioned, like this different notion of distances that will give you different quantum speed limits. When we go in the classical realm, so the band that we look at is the kind of like Mandelstam's stam, and we choose like the length that we define as the reference one. I'm not saying it's the best one, but we choose it from this Burroughs angle from the fidelity. So for the mixed state, I would define the distance as the fidelity for the mixed state, like square root of rho 0 rho t, square root of rho t. I don't want to say this is the good one. And for the classical, for the classical case, again, we also find these speed limits as function of just like the distance. So I don't see, I'm not sure how it translates this uncertainty in the quantum realm to the classical one, because we considered like one kind of distance. I didn't look at the other distance, but I would expect that they, I don't know. My expectation in that is that they would give like some similar classical speed limit, but I'm not sure. I haven't worked it out.
Okay. Thank you.